Today I'm going to make a few comments that I hope you will find interesting. I'll start with one of the challenge problems because I think the construction is interesting, but unlike the hint I gave, this construction uses a non-deterministic automaton. I'm then going to address a question that came up in one of the early discussion threads, but that really wasn't appropriate until now. It concerns whether there are things that can do what a Turing machine cannot do. And finally, there have been several threads doubting one or another form of proof that I have used in class. These doubts are much more reasonable than some might imagine, and so I'm going to try to sort out what needs to be assumed and what needs to be proved. I'm also going to touch on what it really means to offer a proof and have that proof believed. And I definitely don't mean the instructor is always right. Recall that half of language L is the set of first halves of the strings in L. So if L is the two strings, say 0, 1, 1, 0 and 0, 1, 0, then half of L is just the set containing 0, 1. The reason is that for this string, 0, 1, 1, 0, the first half is the 0, 1, and for the other string, 0, 1, 0, it's of odd length, so it has no first half. We want to prove that if L is regular, then so is half of L. And we're going to start with a DFA called A for L. And we're going to construct an epsilon NFA called B, whose language is half of L. So here's how we're going to construct B from A. First, the states of B are pairs of states of A, plus an additional state S0, which is the start state of B. B starts out in S0, makes one epsilon transition, and from then on never returns to S0. And after that, B will always be in a state that is a pair, PQ, of A states, and furthermore, it will make no more epsilon transitions. Here's what we intend to be true whenever B can be in state PQ, after reading the input W. Now remember, B is non-deterministic, so it can be in many such states at once. But first of all, the first state of the pair, P, is the state that A enters after reading input W. So although B can be in several different states after reading W, they all have the same first component, and B simulates A using the first component of A's state. The second component, Q, is a state such that A can go from that state Q to an accepting state of A while reading some input X whose length is the same as that of W. B will be in all states PQ such that Q satisfies the condition I just set. It can get to a final state of A and some input whose length is the same as that of the input that B has read so far. Notice that B doesn't know how long an input string it has read. Finite automata can't count. But we'll work out the transitions of B so that what we want to be true about the second component will indeed be true. The accepting states of B are those pairs that have the same state in both components. The reason this choice makes sense is that if B is in a state, say QQ, then B has read some input W that takes the DFA A from its start state to state Q, and there's also some input X of the same length as W that takes A from the state Q to an accepting state. Thus, if B is in state QQ after reading W, that means there is some WX in L where W and X are of the same length. That in turn means that W is in half of L. Now let's design the transitions of B. From its initial state S0, B goes on epsilon to all pairs of A's states where the first state is the start state of A and the second is one of the accepting states of A. As we shall see, B never returns to S0. And this first move guarantees that the empty string is handled correctly. B accepts the empty string if and only if Q0, the start state of A, is accepting. But that means A accepts epsilon and half of epsilon is epsilon. Thus, B accepts epsilon if and only if epsilon is in half of L. Now we need to design the transitions of B so that after the initial epsilon move, it is only in the states we said it should be in, given the interpretation we put on a pair of A's states PQ. So the transition from state PQ of B on an input symbol A will be to those pairs of states Rs that satisfy two conditions. First, as we wanted, the first component of B's state just tracks A's state. That is, R is where DFA A goes on input A when it is in state P. The second condition concerns the second component. There must be some input symbol B such that A goes from S to Q on input B. Notice the transition is from the new second component to the old second component, so the new second component has a path to acceptance that is one longer than before. Thus, if X takes A to state P, then XA takes A to state R. That's this. We could prove by simple induction on the length of W that the first component of B's state after reading W is always the state A would be in after reading W, but we won't do the proof. We can also prove by induction on the length of the input that the second component of B's state can be all and only the states of A that reach an accepting state by following a path whose length is exactly the same as the length of the input B has read so far. As I said, we're not going to do the inductive proof that this construction works, but I'll set it up for you. Okay. The inductive hypothesis, which we prove by induction on the length of input W, is that B goes on input W from one of its states Q0F, where Q0 is the start state of A and F is one of A's accepting states, to all those states PQ, such that A goes from Q0 to P on input W, and A also goes from Q to F on some input X of length equal to that of W. Once we have the inductive proof, we have only to observe how B makes epsilon transitions from its own start state to each of the states Q0F, and that B's accepting states are the ones with the same state of A for both components. Here's a little example. I'm not going to go over every transition of B on the right, but I invite you to pause the video and study it if you like. First, A is this two-state DFA on the left in orange, and B is the epsilon NFA in purple on the right. From the initial state S0 of B, there is only one epsilon transition since A has only one accepting state P. This epsilon transition goes to the state QP because Q is the start state of A and P is an accepting state. Notice that because A has only one accepting state, we could have dropped state S0 and simply made QP be the start state of B. Now let's consider where QP goes on input 0. Since A goes from Q to P on input 0, that says the first component of the new state must be P. But we also have to look at the second state of QP, namely P, and ask from what states of A are there transitions to P on any input symbol. We see there are transitions to P from both P, which is this, and from Q. It's that. Thus, QP goes to PP and to PQ on input 0. That's these two transitions here. Next, let's see where PQ goes on input 0. First, we consult A, and we see that on input 0, A takes P to P. It's this. So the first component of the new state must be P. Then we ask from what states of A are there transitions to Q. Here we see the only transition to Q in A is this one from P. As a result, the second component can only be P in the new state. Thus, the only transition of B from state PQ on input 0 is to PP. We'll leave the rest of the transitions to you, but notice that the two accepting states of B are PP and QQ, those with identical states in the two components. Now that we know about Turing machines, we can address a question that I recall from one of the first posts on the forum. The questioner was evidently impressed by something called aspect systems. I think I remember reading about them a generation ago. They were supposed to be the next big thing after object-oriented programming. I guess they weren't, but it doesn't matter what they are. because presumably they are some software system, which means they are ultimately executed on a computer. And as we saw, a Turing machine can simulate a computer. We really only dived into the matter of how the storage units of a computer are simulated, but the rest is easy, the arithmetic units, the control logic, and such. The bottom line, no programming system can do what a Turing machine cannot. Real programming systems can do things much faster because the Turing machine is designed to be the simplest possible device that computes, but it's only a matter of speed and not of capability. But another attack on the use of the Turing machine as the definition of what can be done by a computer comes from an entirely different direction. There are those who think we'll eventually be able to build computers that use quantum physics to do things that appear impossible in the world of Newtonian mechanics. In particular, these hypothetical devices behave something like non-deterministic automata, always appearing to guess right. One of the most interesting conclusions is Shor's algorithm for factoring numbers in polynomial time on a hypothetical quantum computer, which is something we doubt can be done on a conventional computer. There have been some interesting experiments in which particles are somehow linked by their spins and carried far apart. A change in one manifests itself as a change in the other, allowing communication over vast distances without any perceptible link. That means, for example, you could not eavesdrop on the communication, so it is more secure than conventional Newtonian communication. I really don't believe there will ever be practical quantum computers. The problem is that a physical device that is needed to represent a single bit in a quantum computer, called a qubit, is huge. I've heard it has to be roughly the size of a refrigerator in order to isolate it from other qubits adequately. But even if we can make really tiny qubits, we are still faced with the fact that a non-deterministic Turing machine is no more powerful than a deterministic one. You should have seen that video explaining why by now. To be fair, proponents of quantum computing claim that while they may not be able to solve anything that a conventional computer cannot, they can do certain things faster. The one big example they point to is Shor's algorithm for factoring numbers. It looks to me like this case is the exception rather than the rule, and the advantages of a quantum computer, if we could ever build one of useful capacity, is small. There are a number of questions about the mysteries of proofs and the logical rules one can use, and a number of these questions arose in a thread about why I claim that one stack, as in a pushdown automaton, could not simulate two such stacks. I didn't prove that point, and in fact it is more than a little vague. What does it mean for one stack to simulate two stacks? If you make a reasonable attempt to combine the action of two stacks into one, you will find you're okay as long as the two stacks push and pop at the same time. Then you can keep in one stack symbols that represent pairs of symbols, one from each of the stacks you're simulating. But two stacks need not push and pop at the same time, and when one pushes while the other pops, you get stuck. There is no sensible thing to do that will represent both moves. Well, if the difference between the lengths of the two stacks is 2, or any constant, then you can remember the top symbols of the longer stack in the state, and only keep the shorter stack and the bottom portion of the longer stack on the single stack you're trying to use. But that's not good enough, because as time goes on, there may be no limit on the difference between the lengths of the two stacks you're trying to simulate. But the failure to prove something is no proof that it can't be done. So the first thing I need to do is to give a precise definition of what would be considered a successful simulation of two stacks by one. I propose that as a minimum, if I had such a construction, I would be able to use it to design one PDA-P that could simulate two others, P1 and P2, and in particular to accept if and only if both accepted. That is, I would have a PDA construction that showed CFLs were closed under intersection. But we already know that CFLs are not closed under intersection. So let's assume that a construction to build P from P1 and P2, as on the previous slide, exists. Then in particular, I could apply the construction to PDAs that accept the two context-free languages that we showed in the lecture have a non-context-free intersection. That is, let P1's language be the set of strings of zeros followed by ones followed by twos, such that the numbers of zeros and ones are the same. Let P2's language be the same, except that the constraint is that the numbers of ones and twos are the same. Let P be a PDA accepting the intersection of these languages. The language of P is the set of zeros followed by an equal number of ones followed by an equal number of twos. Since we assumed we can construct P from P1 and P2, P exists, and therefore its language is context-free, as we know are all languages accepted by PDAs. But we know this language is not context-free. We have reached a false conclusion, so we know that our assumptions are wrong. We have made only one assumption, that P can be constructed from P1 and P2. Since we drew a false conclusion from our assumption, that assumption must be false. That is, we have proved that there is no way to simulate two stacks by one in a manner that is sufficient for us to figure out whether the PDAs using these two stacks both accept a given input. We might be able to simulate them in some weaker sense, but that sense would have to be very weak indeed, and I would not want to think of it as a true simulation, since I couldn't tell from the one stack what both of the, quote, simulated stacks were doing. This proof used a number of logical tools that are sound, but which we might be tempted to question. First, we use proof by contradiction. That is, if we assume some statement S and we use correct logic and true statements to derive something false, then the statement S itself is false. Here S was, you can simulate two stacks with one, in the formal sense of being able to compute the intersection. This is a generally accepted form of logical reasoning, and I don't want to suggest that we should doubt it. Proof by contradiction appears to work in the real world. However, it doesn't really follow from any more basic principles. You need to take it, or something equivalent to it, as an axiom of logic. If you try to prove that proof by contradiction works, you will have to start with something like, well, assume the rule doesn't hold. That is, you need to assume proof by contradiction works in order to prove that it works. An amusing sidelight is that proof by induction, another staple of this course, is also something that needs to be assumed. If you try to prove that proof by induction works, you wind up either using a proof by induction or, what is equivalent, a proof by least counterexample. That is, you say that if you can prove the basis and induction step of some statement, say S of I, and yet S is not true for all I, then consider the least I for which it is false. S of I can't be the basis because you proved that. And if I is not the basis, then you know it is true for I minus 1, and you prove the inductive steps. That is, you know S of I minus 1 is true, and you prove the inductive step, which implies in particular that S of I minus 1 implies a S of I. So again, S of I could not be false. But the idea of least counterexample is equivalent to proof by induction. And it is an assumption. There does not have to be a least counterexample. For example, consider the statement about real numbers is not greater than 0. There is no least counterexample because if x is a counterexample, that is, x is greater than 0, then x over 2 is a smaller counterexample. It is smaller than x, but also greater than 0. Of course, we never suppose that induction works for real numbers. It doesn't. It only works for things like integers, trees, and other discrete things that can be ordered like integers. For these domains, inductive proofs appear to reflect how the world works, so we're okay assuming inductive proofs are valid in those domains. But there's a more worrisome point than the fact that we have to accept some axioms of logic. When I derived something false, I immediately pointed my finger at the assumption you can simulate two stacks with one. This reasoning is important. We use it heavily, especially when we justify the idea of reductions from one problem to another. Definitely, I never proved that assumption about two stacks, so it might be the cause of a false conclusion. But could there be any other assumptions that I used without proof? And could one of those be the cause of the false conclusion instead? I don't think so. I believe everything I used was either proved or I could prove it if challenged, but I could be wrong, couldn't I? No proof is complete and undisputable unless it is written in a very, very formal system. But interesting proofs, such as my claim about two stacks being better than one, are just too complicated to be written that way. In practice, mathematical proofs are accepted by a community using a social process. That is, interested people look at the proof, And if they doubt one or another point, they can challenge it and drill down into the details of why the point is true. Either they will be convinced or the person who claimed it was true will withdraw the claim. That's how mathematics arrives at the truth. I'm going to conclude with a discussion of something that has nothing to do with automata theory per se, but rather applies our understanding of what makes a proof believable to the question of whether we can prove programs correct. There was a paper written on the subject about 40 years ago by 3 computer scientists of serious note. Alan Perlis was the first winner of the Turing Award. Rich DeMilo later became Chief Technical Officer at Hewlett-Packard and was also Dean of Computer Science at Georgia Tech. Dick Lipton was the guy who replaced me when I left Princeton in 1979. He also has a number of important ideas to his credit, including the one I want to talk about now. The paper started by making the points I just made, that you can only believe a proof if good mathematicians have looked at it critically and attempted to challenge any questionable points in the reasoning. In fact, the title of the paper is Social Processes and Proofs of Theorems and Programs. They then went on to draw a significant conclusion. Proofs of correctness of a program need to be subjected to the same scrutiny, or they can't be believed. But proofs of program correctness are boring, and no one is going to participate in the social process needed. Thus, they argued, it was not realistic to suppose that programs of any significance would ever be proved correct. Interestingly, that reasoning is pretty much held up. 40 years later, we still write code, hope it works, fix it if it doesn't, and do not suppose that we can prove it correct formally. There are a few exceptions. First, there has been much more progress than the 3 authors might have expected in automated theorem proving. Computers don't get bored, so to the extent that we can get them to do the checking, we can avoid the social process problem. A second, oddly, is that if you pay people enough, they will do the checking even if they do get bored. So there have been a few instances where a lot of money and time was spent doing a proof of correctness for a non-trivial piece of software. With that thought, I'll leave you folks to finish up the study of Turing machines, and then we'll go on in week 6 to the matter of NP completeness and intractable problems.